Hi, everyone. I think we can wait a few more minutes before starting. So I'll start to share my screen. And I think we can start. Today we are going to listen to a recorded webinar, which is a lecture about chemistry and catalysis and how they can make our society more sustainable. You can find this video on YouTube, on the Royal Institution channel, where you can find other videos about science, math, engineering. So if you like this kind of video, you can take a look on the website. The speaker is Professor Bert Weckhuysen, which is a professor of inorganic chemistry at the Utrecht University in Netherlands. And his work, his research is focused on finding new molecules, new substances that can help us to reduce the concentration of CO2 in the atmosphere. So in this talk, in this lecture, he will explain us how chemistry can help us to be more sustainable, how catalysts work, and how it's and why it's so difficult to convert carbon dioxide into fuels and other chemicals. So I hope you enjoy this webinar.
Good evening, ladies and gentlemen. In the next hour or so, I would like to explain to you how chemistry can help to try to make our society more sustainable. And I have three words: reduce, recycle, and reuse. And these concepts I would like to explain together with catalysis. So tonight, I will explain to you what catalysis can bring us, what catalysis can allow us to do to make our society more sustainable. What I would like to do is to start with a quote, an old quote, a very old quote, but also a quote which has a real modern appeal, a modern concept. Earth to earth, dust to dust, and I changed something, carbon to carbon. And carbon is for chemists nothing else than this black ball, atoms. Atoms which you can connect. And carbon, you know most probably the best from this, diamond. And we always say diamonds forever. However, chemists know better. When you heat this up to very high temperature, then this carbon will be turned into carbon dioxide. And here you see the black atom, ball, carbon, but now it's connected to two oxygen atoms. It's CO2. And this CO2 and carbon, they cycle. And they cycle, and we use it, we reuse it. Nature uses it. Our society is built up from carbon. Me, I, all of you are carbon part at least. 23% of us is carbon. So it's a lot. But currently, we are also having carbon dioxide issues. We know that carbon dioxide emissions are also something that it's harming our society. So why is this? Because since years, we are using another, although you can argue, also a precious form of carbon, fossil resources. This is coal, but you also have natural gas. You have crude oil, which I will explain in a minute. And our society is built from this carbon. We have a lot of materials, plastics, fuels, and all contain carbon. Now, carbon, we use a lot of it. We use a lot of it. Do you know that we use about 90 to 100 million of barrels of crude oil per day? Now, 90 to 100 million barrels, it's about 160 liters. You cannot imagine this, but I just took this here. It's a stadium. It's about 7 of these, totally filled up. So we use 7 of these per day. I'm not talking about natural gas. I'm not talking about coal. So we use a lot. Well, one can say then, do we that now already forever? No, nope. Because carbon, this crude oil, was discovered about in 1850, 1860. And this Colonel Drake, which was actually not a colonel, he discovered the first wells in Titusville in Pennsylvania, USA. And in these first days, people did not know what to do with that black gold. And what you can see in this slide is that it was used for a lot of things. Medical applications, diarrhea, whatever, things to try to cure diseases. The real first application for crude oil was lamp oil to light the houses in major cities like New York. And here in this picture, which I took in the capital of Harrisburg, of the state Pennsylvania, you find this painting. And on the back, you can see statues of where you drill the oil, the crude oil. And in the front, you see ladies holding lamps filled with lamp oil. So this was the first real application of crude oil. So this crude oil was actually replacing the whale oil. So here in this advertisement in the newspaper, you can see that the whales were very happy when the crude oil was used for lamps because they were not suffering anymore. So that is how it started. And then you think, well, lamp oil, I don't think we use this. And then we had Edison. And Edison was the discoverer of this light bulb. So light bulb, by electricity, replaced the lamp oil. And that is how it started. And that is a very interesting quote which I would like to introduce here, that somehow the history repeats. And this is a hybrid car. 1917. This works with gasoline as well as with electricity. Now this car, 1917, the company was stopped its activity in 1918. So one can argue, why this discovery, why this use, why this hybrid car or electrical car did not take off? There are several reasons for. But one of them was that, for example, the early batteries were iron nickel had a problem that when it was winter, they did not function properly, and that it was not properly working when it was cold. And the second is that people did not consider it as very fancy. They wanted to have a car which made noise, because in these days, car racing was getting very popular. So that made it that the car became a combustion engine. In 1900, when you think about the market share, number 1 was the steam engine car. Number 2 was the electrical car. Number 3 was combustion engine car. This shows how the history somehow repeats itself. Now this introduction brings me then to now. This is what we use now. We know cars use fuels. And these fuels are made from this barrel of crude oil. Now how is that done? Well, here I show in this picture the molecule, a very complex molecule. And a very complex molecule is a crude oil molecule, which you will find in this barrel. And this, if you would that put into your car will not ride very long. It will not function properly. And what this is a long, long chain. A long, long chain which I here have been showing with this representation. Black carbon, white hydrogen. Now the first ways was, here I have a barrel of crude oil, and it was already mentioned that distillation can deliver you gin or Geneva, but it also can offer you different fractions. You have to remember, a long molecule has a high boiling point. A small molecule has a low boiling point. So when you heat it up, you can separate it. In the first early years, we only used this upper part, the light, the small molecules. And the bottom part of a crude oil barrel was not used very much. It was waste. Now, over the years, we have, as chemists, as industry, we have been developing ways to cut these molecules into pieces. So when you see here this long molecule, you can use what I put here, a catalyst. And this catalyst is nothing else, something which allows you to break this bond. And by breaking this bond, this piece, you can put into your car and you can drive with a combustion engine. And what is now this catalyst? What is now this scissor? This device which allows you to cut up this molecule? Well, that's nothing else than this powder. And this is a catalyst. A catalyst is a substance you add to a reaction mixture and which will accelerate, speed up a process. It provides almost literally the scissors to cut crude oil or molecules in general into pieces. Now this thing where you have crude oil, where you cut it, it's interesting to know that in the beginning the catalysts were not that great. In the beginning the catalysts actually, they produced fuel which was not that good yet. It also smelled badly. They had to add vanilla to it to get it better smelling. But over the years, I hope you admit, we don't have anymore a vanilla taste or smell because we have been developing better catalysts which are able to use now every carbon almost of this barrel of crude oil. So this is how the crude oil, how the oil refinery, how we have been using our fossil resources to make our fuels, to make our plastics, to make our medicines, and also to do this. This is a picture from LA, Los Angeles, America. And you can see that you have here this brownish background. Smoke, formation of bad air. And that brings me to a picture from a long time ago. I'm the one in that red circle. And this is, on the right, actually a fake picture because in these days we did not have colored pictures. It was black and white. These things are trees which are dying. Trees are suffering from acid rain. However, if you would ask my children nowadays if they know what is acid rain, I doubt they know it because we majorly solved the problem of acid rain. What is the reason why we had acid rain? That is because in this barrel we have not only the hydrogen and the carbon, but other elements. Elements like sulfur and nitrogen. And we have been removing this sulfur, by making sulfur-free fuels, transportation fuels. And we have been removing the nitrogen because we have introduced a device. And the device which we have been using or introducing since the 1970s is this. And this is an old one, as you can see, 40 euro, I bought it. And this device is nothing else than at the end, between the engine and the exit of the outlet of your car, you put this device, which is a catalyst. And here you have noxious gases and harmless gases coming out. So you convert something which is poisonous to non-poisonous. If you would open this device, then you would see this honeycomb type device where you see you can go through and you can see through it. These holes are filled with material, with catalysts, which are able to bring in the noxious gases and transform them in non-noxious compounds, chemicals. I would like now to explain a bit what is a catalyst. But so far I just talked about a powder. So this is this device which I have in my hand. And now I would like to introduce to you some of the molecules and how a catalyst works. Catalysis is nothing else than surface chemistry. Chemistry at surfaces. And a surface is here, this floor, solid. And my shoe is solid, solid, solid. You can also I have water here in my hand, it's liquid, solid. Or here, this gas is air here, it's a gas, solid. So here we have processes going on at surfaces. And these surfaces, they are reactive. And you know it from corrosion, from rust. That's nothing else than a surface process, where a surface is covered by iron oxide. Now here the same, so here we have different compounds, molecules, and I brought these molecules with me. Here I have a box with some molecules. So for example, when you have the noxious compounds coming from your car engine, is this molecule, which is CO, oxygen red, black is carbon. And here I have my CO2. Do you want to make out of this? Carbon, oxygen, oxygen. But there are also other noxious compounds besides CO, and it is NO and NO2. Here now I have a blue nitrogen, oxygen, nitrogen, oxygen, oxygen. This one gives a brown color to the air. It's also toxic, and you want to remove them. So if we want now to remove these, and we want to make non-noxious compounds out of it, such as water and nitrogen, then we have to do something. We have to do something because we want to convert them. And the first reaction which we want to convert is the reaction where we have CO plus oxygen gives CO2. So what I did now is I put here a big plate. And this plate is nothing else than the surface of a catalyst. And on top of it, I put a metal nanoparticle. Now, I would like to dive into the world of molecules and atoms. I want to dive into the world which is really tiny and small. So this plate in reality would be 4 nanometer, 4 nanometer. Nanometer 10 to the minus 9, it's a 1 billionth of a meter. You can think, what is that now all? So take a plane from London to New York. That's a long distance. But what is then 1 billionth out of it? It's 0.5 centimeter, 5 millimeter. So this then is 2 centimeter, 2 centimeter in the scale from here to New York. Pretty small, you agree? And this ball is 1 nanometer. That's small. And here everything happens. So what happens is a reaction where CO plus oxygen reacts and makes CO2. So that's the first reaction, which is removing the noxious compound CO from the exhaust catalyst, as I show you in this picture. The second reaction is a reaction where we have to remove this NO, nitrogen oxide. Now, if we would do that with oxygen, that will not work, because then we make an even worse molecule, NO2. So this NO, we have to react with CO, they combine, and they make then nitrogen, and that is non-noxious. So this is the catalyst which cuts and pastes, which is a scissor, but also which is bringing molecules together. So that is something what is happening, and we have not only this ball, we can also put another ball on it, another particle. And I forgot to tell you that this particle is made out of noble metals. And these noble metals, as it states, is very expensive. Platinum, rhodium, palladium. Now this ball contains 55 atoms, and 13 of them are inside, does not see the surface. Remember, I told you about surface chemistry. So what happens is the chemistry happens at this surface. So we want to make these particles pretty small, because then all the atoms are surface atoms. But you can also notice that they have facets. And these different facets have different reactivity towards the molecules. And that means that catalyst scientists, they are searching for the right particle, right in terms of size, right in terms of these facets exposed to the air, to the molecules it wants to destroy. So this is surface chemistry. This is catalysis. And I already explained that these are my children on the left. And they are at holiday in 2017, and this is a picture from LA last year. But you still see that it's not yet right. You can still see that this is not where you still would like to live in 2100, no? We still have to do something, because this pollution also means that we will have to try to avoid things like the CO2 rise, which leads to, for example, the melting of the ice and the level of sea levels which are increasing. And now the molecule is not NO2 or SO2, but CO2. And we have now to make a new device, a new type of catalyst, a device which allows you now to take the CO2 out of the air and convert it in something useful, something where we can really try to do this recycling of carbon, carbon to carbon, CO2 removed. Now one could argue and say, well, okay, it's not my business. So this is a picture which I took in the plane when I was flying to Canada. It's a flight to Calgary from Amsterdam. It was one with a flight with one of the most fuel-efficient planes. And what happens is that you are, of course, using fuel which comes mainly still from this barrel of crude oil. The emission, CO2 emission, from here, or let's say Amsterdam, going to Calgary and back, is 1 ton of CO2. Okay? A Dutch, and I think also a UK person, emits about 11 tons CO2 per year. I think, okay, 11 tons. I have also to say that every day you breathe CO2. Remember, you build up from carbon. You eat carbon-based products. So you will have as exhaust CO2. So it's about 1 kilogram per day. So about, depending on the person, 300 to 400 kilograms CO2. You cannot do a lot about it. That are the facts of life. When you drive 35,000 kilometers, 5 tons. You see, it adds up. I'm traveling a lot, so it means I'm a big emitter. People in the US and Canada, 16, 17 ton CO2 per year. On average in the world, 5 ton CO2. Yesterday, I came here by train, left Utrecht and went via Brussels to London with the train. Well, the first thing is that you can see that here you can notice that it was indicating that it was CO2 neutral, at least claimed by the train company. So that means that we have been not emitting CO2. And as you can read, it's indicated that the electricity comes from wind or solar panels. The first observation is that the price coming by train was more expensive than taking a plane from Amsterdam to London. That's surprising. And that is because we have to admit that we do not take into account the whole price. That means that somehow it's strange that we pay more for a ticket by a train than with a plane. And the part of the reason is that our legislation does not take into account any, and not yet, the CO2 emissions. It does not treat CO2 emissions as something really important. So the question is, should we do similar to what we have been doing for introducing the catalyst, exhaust catalyst, which was introduced by legislation? Maybe it's time also to consider if we have to think about legislation which helps us to make this transformation happening. So this electricity comes, for example, from wind and solar panels. Now, we also have to see to take this picture into account. And what I want to say with this picture is that the sun not always shines. You have fluctuations. In the summer, the winter, day and night. And the wind is also not always blowing. And it depends really locally if you have really good electricity production or renewable electricity production. Secondly, you may not forget we still have to reduce, because we still have this molecule in our air, 400 ppm. So we have to reduce it. So how do we do that then? So we have to try to reduce the CO2 and convert it in something useful. And for this, I would like to state that we have now this molecule, carbon dioxide, which has one carbon. And remember that this molecule, for example, is what we currently use as a fuel molecule, which consists of many of these carbons. You agree? So we don't need, at this stage, this, but we need something to glue carbons together. So the catalyst should not be a scissor, but something which brings together carbons, and carbons which are linked together and makes a new molecule. For this, I have an experiment. I'd like to show you a short experiment to illustrate what I want to say with this. And I start with water. Water, easy. So I think I have here somewhere. This is water, this is oxygen and hydrogen. So take a bit of this water. I forgot. So, but water is still okay. So we fill this with water. You have to believe me, that's not a gin. And now I have CO2 with me. Now I could take here the CO2 from the air at 400 ppm. Then I need some kind of vacuum cleaner to bring the CO2 and try to bring it here, which is not so easy. So I have another form of CO2, which is the solid form of CO2. So this is solid CO2. What you can do is you can add it now. And now you see that CO2 is released. We have to add a catalyst. And this is catalyst. So we can add a bit catalyst. And now, out of this, we make molecules. And one of the molecules which you can make out of it is, for example, methane. And that is a hydrocarbon, which you can use for certain things like heating. And even you can use it for driving a car. So, I would like to continue now by showing what you can do with this CO2, because this experiment where CO2 and water with a catalyst is giving something is already reality. I went some weeks ago, I went to Germany, to Werther, near Bremen. And there you can find this plant. They use from CO2 from the Bremen city, and they brought it there in a small village or city of Werther. And there, with a catalyst, they converted to e-gas. It's gas made from electricity. And this is the reaction where we have CO2 plus hydrogen gives methane. So what you have is nothing else than CO2 plus hydrogen gives this molecule. And this is a reaction which currently works. You can argue and say, but if we have this already, what prevents us then to implement it? Well, the factory which I showed you there in Bremen is currently not making a lot of profit. Again, because of legislation. Again, because it has to compete with these fossil resources, which are much cheaper. So that is where we are working on. We want to work on this reaction to make more efficient catalyst particle to enable this reaction, but also we want to make sure that we make other molecules out of methane. Because methane is useful, but it would be wonderful if we could make the materials which we currently use which we currently make out of, for example, this barrel of crude oil.
This black box produces a sustainable fuel from CO2. Right now, society mainly uses fossil fuels to produce our chemicals, fuels, and electricity. Basically all synthetic products we use every day. By burning fossil fuels, carbon dioxide is released, and we're rapidly warming up the Earth. We want to replace fossil fuels by sustainable resources, for example, renewable electricity. But the sun doesn't always shine, and consequently, we'd like to be able to store large quantities of its energy, for example, in summer, to be able to use it in winter. In my PhD research, I want to solve both of these problems: carbon dioxide emissions, as well as the current difficulty to store electrical energy on a large scale. There could be one solution helping to solve both of these problems: using CO2 and sustainably produced electricity to produce other molecules, such as methane. If we use CO2 from point sources like factories, together with hydrogen that's produced by splitting water using renewable electricity, we can make methane. This conversion is enabled by a catalyst. In my research, the catalyst is a nickel nanoparticle. Nickel is a cheap and widely available metal, as opposed to noble metals such as platinum, on which this reaction also occurs. We try to use sustainable materials to facilitate the transition towards a green, circular economy. In the next coming years, we'll investigate how to create other value-added chemicals from CO2, like methanol or ethylene and propylene. This way, in the future, we may be able to use CO2 as a sustainable fuel.
If research, like what Charlotte explained, can become a reality, then this girl in Beijing can take off her mask. But that is one part of the story. One part where we want to reduce and recycle our CO2. But we also make other waste. This is something what you have in your kitchen. At least this is what we have at home. And this is made out of polymers, biopolymers. Polymers like cellulose, and here I show you lignin. Now, what is a polymer? A polymer is nothing else than a repeating unit. And that repeating unit is shown here. So a biopolymer or a polymer is a unit which you can just continue. Works. Which you can continue. And here, long chain of this. This holds for lignin, cellulose, hemicellulose, chitin, and these have now also to be cut in pieces. This lignin you cannot eat. Therefore, it's not in competition with food. And if you can cut this in selective in pieces, then we can make materials out of it, which we want to use. And that is shown here. On the right, you can see a reactor. And I put that brown powder lignin in the reactor together with a catalyst, a scissor. And you can see that wood can be completely converted into molecules which you can use for building materials. So what you have is nothing else than wood, where out of it you take this compound which is not eatable, lignin, and that can be decomposed, cut it in pieces with the right scissor. And you can imagine that you don't need anymore this scissor for the crude oil, but you need another scissor like this one. So this allows you now to cut these things in pieces and make these monomers out of the biopolymer. Now this holds not only for the lignin, which I explained in this slide, but also for chitin. So that are, for example, coming from shrimps. And this is giving strength to the species, like the lignin gives strength to the trees. Molecules which give strength, biopolymers. And those you can now use to make functional materials out of it. That means that you want to recycle. And that brings me to the first thing which I want to show here. I want to connect it. Catalyst together with recycle.
Wouldn't it be great if the paint on our wall would be able to fix pollutants from the air?
Inspired by nature, we can design coatings which are both sustainable and have special characteristics. Most coatings, such as paint, are produced using a fossil feedstock. To contribute to the transition towards a circular economy, we research how we can reuse bio-waste, turn them into a green feedstock for coatings.
Take, for example, wood. Wood contains a compound called lignin that gives wood its structural strength. Lignin can be isolated from wood waste and be used as a base material.
Another possibility is a building block called chitin, which is found in the shells of shrimps. It has a function similar to lignin. It gives crustacean exoskeletons their strength.
In our lab, we break down the wooden shells and turn them into small chemical building blocks. We use the lignin and chitin to turn them into long bio-based molecules, biopolymers. We then grow the biopolymers into thin films, providing us with novel bio-based coatings.
But that's not our final goal. We want to be able to make smart coatings, coatings that have special functions.
For example, a coating that's able to store, filter, or convert gases. We design those functional coatings using molecules mimicking processes found in nature, like fixing pollutants from the air, such as formaldehyde.
The coating itself would then serve as a catalyst, enabling or fastening chemical reactions. When applied to the wall, the paint can convert pollutants from the air into harmless compounds, using energy from the sun.
We study model systems of such novel coatings. With the use of highly sensitive microscopy and spectroscopy techniques, we can map the chemical composition of the compound on the nanoscale over the entire surface.
When we fully understand the chemical identity of our material, we are able to tailor and optimize the functional coatings of the future, made out of recycled bio-waste.
But besides making use of these biopolymers, chitin, lignin, you can also make CO2 and convert CO2 to another molecule, which is methanol. All this waste, which I just already showed, can be converted into this simple molecule, which is methanol. And here I show you methanol. Methanol, carbon, oxygen, hydrogen. If you now take this molecule and you glue them together, you can make almost any molecule which we currently use to make our materials, fuels, and so on. So how you do it? Well, here you have a unit, a plant, a chemical plant in Belgium, in Fillouis, where you have a catalyst, which is shown here. It's a zeolite. And that allows you to have this molecule converted in this catalyst material into two molecules which are very important for our society. The first one is propylene and ethylene. Carbon-carbon double bond, carbon single bond, carbon double bond. These two molecules are the basis for plastics, the basis for a lot of our materials which we use. And this is done, here are these molecules, and this is done in a process which is called a surface polymerization reaction. So this molecule will be adsorbed on this surface of this ball and then growing and making a chain. Now, this catalyst is a bit a special one. Polymerization catalysts are special in the sense that they become part of the product itself. That the catalyst at the end is in the product. Again, in small amounts, ppb, ppm levels, but it's there. So that means that when you convert in these huge polymerization reactors on the left, and you make, for example, the plastics which you can find, for example, here in this tube, it's polyethylene, then here this material will contain some of the catalyst material at the end. And that has consequences. But this can be done, and it means that you have to try to do something where this methanol is not anymore made out of these fossil resources, crude oil, coal, or natural gas, but you try to make alternative use of, for example, CO2, of biopolymers or material which comes from the earth and you can recycle. So that brings me to the second piece, which I want to add, reduce. You want to reduce our CO2 footprint. You want to reduce the use of fossil resources.
This bottle contains methanol, a small simple hydrocarbon with an important role to play in our future global economy. It serves, for example, as a key building block for producing various sustainable plastics.
Right now, these materials are mainly obtained from crude oil. To be able to make plastics from crude oil, these long molecules first have to be cut into smaller pieces or chemical building blocks. This is done in a chemical process called cracking, which consumes a large amount of energy.
Currently, methanol is predominantly produced from fossil fuel-based synthesis gas, a mixture of carbon monoxide, carbon dioxide and hydrogen. Alternative, cleaner and more sustainable routes are being investigated. For example, chemically recycled CO2, biomass and even waste can either be directly or indirectly transformed into methanol.
Methanol can be converted to two small molecules which can serve as feedstocks for plastics, ethylene and propylene. This conversion is enabled by a catalyst. In my research, a catalyst is a zeolite, which is inspired on a natural mineral. It contains tiny pores and tunnels in which the methanol is reacting to larger molecules.
The type of molecules that are being formed are depending on the size and shape of the tunnels and on the active parts of the zeolite. The next coming years, my research is focused on improving the efficiency of the process with the least amount of side products.
With the ethylene and propylene that Sophie is providing, I in turn focus on the synthesis of value-added products such as polyethylene and polypropylene, more commonly referred to as plastics. With both having various applications in today's society, it's becoming increasingly important to understand the underlying chemistry here, as well as derive these materials from green and renewable feedstocks.
But plastics have also nowadays another name. They also are felt that we somehow are polluting our sea. News coverage indicates that you find parts of this plastic, small parts of this plastic, micro and nanoplastics, in, for example, seafood, fish, and then we eat it up, and we can also find it then in our bodies. So we will have to do something with it. We will have to do something with this plastic. We will have to make sure that we think about reuse, that we try to make cycles for this carbon, for this plastic, where we try to make the products of the future in such a way that we do not pollute anymore. Carbon to carbon, circular economy, circularity. So that means we will have to make sure that we do this reuse. And that brings me to my last piece of the puzzle. This has to be added. My excuses. That was the risk. So I don't know if we have to cut that out of the movie, but that we will see. Reuse. This here indicates that we have now reduce, reuse, recycle together. And here you see catalyst centrally placed into this picture. Why I put here the catalyst central? If we think about trying to make our world circular, trying to resolve these issues where we, for example, make sure that we can live in a society which is circular, where we think that end-of-pipe technology, like this exhaust catalyst system, is not where we have to go. That means that we'll have to think about new systems, new catalysts to make this possible. And here I show you some different glues. Different glues to do that, different catalysts to connect molecules together. You can also think about these three scissors. And I have here some paper. So this is one, and this is one. Let's try this one. Should take this one. So if this is a catalyst and this is the substance, this thing, but you have these molecules you have to convert, that works, but I hope you see this is moderately well done. That goes still fast, but this one is more cumbersome, as you can see. And I'm not faking that now. And this is where it was really made for, no? See, this goes rather straight. And the point I want to make with this is, if these are our molecules, what we have to try to convert, and these are the catalysts, the cutters or the scissors, to try to cut molecules, or that you have this glue to bring molecules together, that means we will have to have insight what is going on in this catalyst. And that brings me to the field where I'm working, because what I'm trying to do is, I'm trying to use as a detective this kind of magnifying lens of glass where I try to understand what is going on. Because the world of molecules and atoms I want to make visible. And why we want to do it? Because if we want to design the new catalyst of the future, we have to understand how these things work. We want to really master, design this new catalyst. So that means you will have to be able to see molecules. And we have modern methods, for example, to do this. And every flash you see here is a single molecule. This is chemistry visualized with powerful cameras at the nanoscale, at a very small level of atoms and molecules. And you can do even other type of methodologies to do that. And you can think about a system, like if you go to the hospital, you can have an X-ray scan. Now we have modern equipment where you can really zoom in at the catalyst particle. And here I show you a movie of what we can do with current, powerful X-ray microscopes, where we can detect almost any element of the periodic table. And these things can be combined. And you can now visualize a catalyst particle in 3D. And here I show you such a catalyst particle, 3D printed. This particle has the size of the thickness of my hair, 50 micrometers, very small. You can see what you can now do. You can really look into this particle down to the nanometer scales. And that is what we currently do. And we can even then dive into a molecule and see the internal structure of a catalyst. And with this kind of insight, we hope to make the catalyst of the future. But the real catalysts are maybe not the catalyst we devise. The real catalyst is the knowledge as a professor we transfer to the next generation. We, as professors, have to train the new students, the new people who have to do this job, to really make this transition possible, to really make that in 2100, their children will not talk anymore about the CO2 problem, so that the CO2 problem is solved. Thank you very much.
Okay, so the webinar is over. And it's a webinar, so Professor Bert Weckhuysen is not here to reply to our question, but if you have some question or curiosity, we can talk about it. We have five more minutes to talk about it.
Ciao, this is Giovanni. I have a question about the catalyst to make methane from carbon dioxide from the atmosphere. Does it already exist a technology that can be planted in a field to catch CO2 from the atmosphere and produce methane at this moment?
I don't know, because of course it's not my research, so I don't know if there is a technique now that is able to convert carbon dioxide.
Because I've seen in the video there was a laboratory equipment on a small scale.
Oh, okay, on a small scale, yes, of course. In the lab, yes, I saw that in the lab of Professor Weckhuysen, they do it every day, but on a small scale. But on a large scale, I don't know.
Well, because I think it's already testing on Mars with the latest rovers. There have been some apparatus that they're exploring to do this on Mars, because there is an abundance of CO2,
okay,
and methane is needed as a fuel to come back to Earth. So they plan to send robots to make fuel from CO2 first, And when there will be enough fuel to come back, then they will send humans. So
Okay.
it's a very ambitious project. Would be nice to test on Earth first.
Yeah.
You know,
Of course, that would be
get
great.
rid of CO2 from the atmosphere would be nice. Okay, thank you very much. Anyway,
You're welcome.
bye.
Bye. So, are there more curiosity? Okay, if there is none, we can close the meeting, and I'll see you next Thursday with biology invited webinar. So goodbye everyone, and have a nice day.
Bye bye.
Goodbye.